Once upon a time, there was this physicist named Hans Christian Oersted who observed a very peculiar thing happening, or I would rather say that it was peculiar to him at that time. So, what he observed is that there was a wire kept on his table beside which there was a compass like this. So, he was performing some kind of electrical experiment in which a current was supposed to pass through this wire at some point of time. So, as this current was passing through this wire over here, he saw that there was a deflection in the compass needle. So at first, Oersted thought that maybe there was some kind of magnet near this compass. So he started searching for the magnet, but he found none because there was really no magnet near the compass. But still, there was deflection in this compass needle. So this was very astonishing to Oersted that how come this is happening. So he thought of doing some kind of a lab experiment, a proper lab experiment to study this peculiar thing that was happening. So what he did, he took two stands in his lab. Let me draw the situation. He took two stands like this, and he kept a wire over the stands in this way. And then he took a compass needle which was initially facing north when this wire was not connected to any kind of battery. After this, Oersted took a battery and connected it to this wire in this way. So as and when Oersted connected this battery to this wire, a current started flowing in this wire, and this compass needle got deflected in the left direction, that is towards the west. So Oersted thought, okay, so let's perform, let's go on experimenting with this thing. So Oersted reversed the battery, and the situation got somewhat like this. Yes, he reversed the direction of the battery like this. Again, there was this compass needle which was initially pointing towards the north. So at first, when there was no current in the wire, there was no deflection in the compass needle. But again, when he connected this wire to this battery, current started flowing through this wire in this direction, and this compass needle got deflected towards the right side, that is towards the east. So Oersted concluded that there must be some kind of magnetic field that has been created due to the flow of current in this wire, due to which this compass needle is deflecting. So he concluded that a current carrying wire or conductor, anything you can see, a current carrying conductor produces a magnetic field around it. So he concluded this because there was a magnetic field which was created due to the current flowing in the wire. This magnetic needle was deflecting towards the right or the left according to the polarity of the battery over here. So this was a pretty simple and cool type of experiment which Oersted performed. But this simple and cool experiment was a revolutionary experiment which changed the course of study of physics, and it introduced the concept of electromagnetism. Oersted experiment, by which Oersted had already concluded that there was some kind of relation between the study of electric charges or current and study of magnets. Now there were two physicists named Jean-Baptiste Biot and Felix Savart who started performing a series of experiments on different shape of current carrying conductors, the purpose of which was to find a formula for magnetic field that was being created due to the flow of current in these conductors. So what they did is that they took a conductor. Okay, let me just use a different color for this one. So they took a conductor, say XY. They took a conductor in which a current was flowing in this direction, I. Now what they did is, or what they wanted is to determine the value of magnetic field at a point anywhere here. So let's say this here, a point P. So they wanted to find the value of the magnetic field over here due to the current flowing in this wire or conductor XY. So you may be thinking that why I gave this cross sign over here. So let me just explain it to you separately, that what this cross sign means. So the cross sign in study of magnetic effect of current will always mean a magnetic field which is perpendicular to this plane of paper, that is where I'm writing, and into the plane of paper. So this denotes a magnetic field which is perpendicular to the plane of paper and the direction is into the plane of the paper. And if I write or give a sign like this, a dot, then this will always mean that the magnetic field is perpendicular to the plane of the paper and coming out from the plane of the paper. So Biot-Savart thought that it would be convenient to assume that the magnetic field was actually made of contributions of small segments from the wire. So they considered a small segment of wire like this, DL. Now this thing over here, DL vector, is actually called the current element, which denotes the length DL of this small segment of wire and the direction, which is the direction of the current in this small segment of the wire. So the direction of current in this small segment of wire is upwards like this. So this is the current element. So we will always refer this as the current element from now onwards. Now you drew a line like this and we give a vector R, which actually denotes nothing but the displacement and the position with respect to this small current element dl. So actually this is a position vector with respect to position vector of p. I would say position vector of p with respect to this current element dl. Now he considered this point at an angle theta from this dl element. So let me draw the axis of this current element dl. So it was considered from this current element at an angle of theta. This point was considered. So now he performed many kinds of experiment and then he concluded that the magnetic field value over here is actually directly proportional to the current flowing in this conductor. You may be thinking that why I use this dB, because we are considering a small length of this wire dl, due to which we are finding the magnetic field. So due to this small length of the wire, the magnetic field over here would also be small, so we are denoting that also with dB. Now he found out that this magnetic field over here is directly proportional to the current that is going through this wire. And then again he concluded, or he found out, that the magnetic field at this point is directly proportional to the current element. There was another thing he concluded, that this magnetic field value over here is actually directly proportional to sine theta. And another thing he concluded, that this magnetic field is inversely proportional to the square of the distance between this P and this current element dl. So combining all these things, combining the above factors, what Biot-Savart said is that all the things are actually can be written like this. Right. So if I just remove this proportionality sign, I need to write a constant. Now this constant over here actually depends on the medium between this point P and the wire. If it's air, it can be somewhat different. If it's water, then it will be somewhat different. So the value of K will vary if we vary the medium between this P and dl. So in case we are considering free space or just air, if you tell, then this value of K is nothing but K is actually mu naught by 4 pi, whose value is 10 to the power minus 7 Tesla meter ammeter inverse. This is the value of K. So we can write this thing as dP equals to mu naught by 4 pi into I dl sine theta by r square. So finally, Biot-Savart actually gave the expression for magnetic field which is created due to this current carrying conductor xy.